before we do something new, allow me to see if what we talked about yesterday sank in. And this is just a quick little kind of test circuit. Trying to do a better job of drawing these a little bit neater. I'm going to add a switch somewhere anyway, so don't hurry, but I'm going to put a resistor on one side and an inductor on the other. This is one way to create a circuit that will discharge an inductor. Again, not a particularly interesting circuit, but a circuit nonetheless. And because we've done a little bit of work, let's put a few numbers to this. And I'll put a starting switch here so we have some place to start. Switch 1, switch 2, and switch 3. So we got a good picture of it? All right. So at time 0, I want to close switch 1 and switch 2. All right? Everybody understand? Can you tell me the current through all 3 circuit elements shortly after I close switch 1 and switch 2? Should be cake. Take a minute and do so, please. So if saying the words close the switch is not enough for some of your less imaginative minds, there, those switches are now closed. So it should be very clear, 2 amps, 10 volts, and 10 volts. This is a very straightforward 2-resistor circuit. The resistances are the same. At this point in the year, seeing that the resistors are of the same value should automatically conjure in your mind that the voltage is evenly split among them. You should be able to reach that point fast. Very simple circuit. Now, we're going to close switch 3, and let's say that closing switch 3 is a new time 0. All right? I'd like to know 2 things. What will be the voltage and current across all the elements of the circuit at time 0? And what will be the voltage and current across all the elements in the circuit after a long time has passed? So close this down. And that's now time 0. Think it through. But I'm going to be calling on a few of you to figure out what to do here. I don't think the answer is obvious. But it's not terrible. Just look at your notes from yesterday. That should be enough. And the whole point here is to recognize that we're not looking at the transitional portion, not what we solved for yesterday. We're looking at the instantaneous time 0, the moment switch 3 is closed, and the steady state condition. How do inductors behave under those circumstances? Draw 2 circuits, real quick. Just a quick sketch. All right, we should be about done here. The inductor behaves different. If you didn't write it down, I'm disappointed. And I'm not walking around to see who you are, but I will be. The inductor acts as if it has infinite resistance at time 0. That's the whole point. The back EMF prevents the flow of current. So when you first close the circuit, there's no change in the circuit. It's as if the inductor is not there. No current can pass through it. The steady state condition, though, presents the opposite. In the steady state condition, the inductor presents no resistance to the flow of current, which effectively cuts off the other resistor because they are in parallel. This is the steady state condition. Now, that makes that pretty easy, right? 2 amps, 4 amps, 20 volts. This circuit transitions. Now, the method in which it transitions isn't, Now, at the steady state condition, there's effectively no voltage across this portion of the system. But there's clearly energy being dissipated by the inductor because we have current passing through the inductor. And that suggests there's probably going to be some kind of energy storage in the inductor, similarly as we have energy, stored in the capacitor. So if you wanted to use that energy, well, that wouldn't be so bad. You just open this switch. At the time where we're at the steady state condition, at that moment, the inductor has its maximum current passing through it, which is currently 4 amps. Right? There's going to be 4 amps passing through the inductor in this circuit. Although I didn't draw the inductor in there, that was for demonstrative purposes for the people who were dealing with the resistance. This is what the circuit looks like after the long term, where this has a resistance of 0. This is our 5 ohms. So there must be 4 amps passing through the inductor. It's in series with a resistor that is also seeing 4 amps of current. If I open this circuit, there's energy in the inductor. Suddenly that energy has a place to discharge because it is connected to a 5 ohm resistor right here that would allow the current to continue its journey now through this resistor until the energy is dissipated. Everybody follow along? Interesting question. What will be the EMF instantaneously when we open this circuit? Can't be 0. Although that seems like a reasonable thing because it's 0 right now. I mean, it's 0 before you open that switch. There's going to be an EMF in the line, right? There has to be. The collapse of this current is going to produce an EMF. But remember, there's current passing through the inductor. When I first opened this switch, what was the last current passing through the inductor? How much? 4 amps. That 4 amps is going to attempt to be preserved by the inductor. So the initial collapse of the field will continue a 4 amp current.
Would it diminish?
It's going to have to diminish, yes. So we'll have to talk about the discharge of an inductor.
Would it ever actually be a 4A, or would it just be really close to 4A and start there?
Well, the moment we open the circuit, it begins diminishing immediately. So we say instantaneously, at the moment that circuit is opened, it starts at 4 amps. In the same way that a capacitor that's fully charged starts with the voltage that it has at that moment, it immediately begins to dissipate. Same thing here. Now, guys, this would have to be true in order to maintain the symmetry of the system. Symmetry is the wrong word. But to maintain what's happening in the system, there's 4 amps passing through the inductor that represents the EMF that's going to generate when the inductor begins to collapse. It has to start by producing that same 4 amps that was there initially. We're not going to have a discontinuity because we opened the switch up here, because we have a place for that current to continue to move. Now, we should talk about how to deal with the discharge of the inductor to get a feel for it. But this is one way to do so. Now, there's not going to be 4 amps there very long, by the way. You recognize that it's going to discharge through that resistor all of the energy that happens to be in the inductor. I want to do a bit of a segue before we go on to the next part. Something that I think will benefit all of you a little bit, and it's a nice reminder. I want to talk about 2 circuits for a minute. I did not do this earlier in the year. I feel like today is a good day for us to do this. It'll only take a moment. So consider these 2 circuits. simple. I have a EMF here, resistor, capacitor. EMF, resistor, capacitor. Oh, inductor. Sorry, inductor. Let's assume that these circuits represent time zero. I've closed the switch, and we're starting from time zero to the point where they are in their steady state condition. And we're looking at some moment in there. You'll remember that the charging equation that we developed by looking at Kirchhoff's law, and said that using Kirchhoff's law, we could write an expression that we could then find a way to solve for an expression for the charging or expression for the current. Sound familiar? One thing we didn't do first semester, which I probably should have, but I didn't think to do it. The amount of energy that's being consumed by this circuit is defined as the amount of energy being produced by the EMF. Meaning the battery has both a current and a potential difference that's being created and supplied due to whatever mechanics the battery is using. So if that's a standard alkali battery, then we're talking about some kind of acid reduction relationship. If it's a power supply, then something else is producing this EMF. But the power delivered to the circuit is voltage times current, right? First semester. I don't know if you know this, but if we take this relationship and multiply both sides by the current, we get an equation that is now the power distribution of the circuit. You see that? Because the left side is the power being delivered by the battery, current times voltage, which means this has to be I squared R, the power being dissipated by the resistor, and this Q over C times I has to be the power being consumed by the capacitor as it charges. Everybody follow that okay? So I don't want to come back to that. And I'm not looking at Oliver, but Oliver, you understand that that's what we're talking about here now, right? Because I want to build on this, and in 10 minutes, I don't want to come back. So is everybody else good? So I didn't mean to single Oliver out, but we have a history. Yep.
So Q over C times I is how much charge the capacitor takes to charge up.
No. Q over C times I would be the instantaneous power being consumed or used by the capacitor.
Would it be stored?
It's probably being stored, but it would be the same if this was being discharged. So I don't want to say which state we have to be in for this. You'll understand in a minute, I think, but it could be either one. For right now, in this circuit, it would definitely be being stored. Everybody okay so far? This one's easy to believe because we've been using I squared R the whole year. This one might be less so, but follow along with me for a minute. Power for the capacitor is Q over C times I. Power is defined as the rate in which energy is being used, right? du dt. I'm using U as a generic term for energy. Is that okay for all of you? Well, that means this side is Q over C dq dt. Right? Now, I'm going to switch this Q to the lowercase q on purpose because we're somewhere in the middle of the charging of the capacitor. So I'm using lowercase to indicate I don't know how much charge is on the capacitor. Is that okay with all of you? Rules of algebra still apply here, so I'm going to multiply both sides by dt. And I get du equals Q over C dq. I'm not looking at power anymore, but if I integrate both sides, it should tell me the energy stored in the capacitor. if I go from 0 to U max, the total amount of energy, that will be when the capacitor goes from 0 to full charge, Q max. Does that make sense to everybody? So this side is just U max. This is a pretty simple integral, isn't it? I can factor out the 1 over C. And I have the integral from 0 to Q of Q dQ. So even a non-calculus student should know how to do this because we've done it. This is a polynomial. So increase the exponent by 1, divide by the new exponent. Still good? All right, so this is not a surprise. We've used this before. This is 1/2 Q squared over C. And if you use Q over C equals V, you can probably come into a few other versions of this, right? 1/2 CV squared and so on and so forth. First semester. I never derived it in class. This is how it is derived. So, do you understand what we're probably going to do next? How much energy is stored in an inductor circuit? Doesn't that seem like a reasonable next step? Make quick current loop. EMF minus EMF for the resistor minus EMF for the inductor has to equal 0. Right, Kirchhoff's laws. Or the battery equals I times R for the resistor plus, and an inductor, if you'll recall, is L times di dt. Maybe multiply both sides by I. You still okay? No worries? Yes? No? I'm not going particularly fast, but since so much of this is the same, this is my power generated by my circuit. So this must be the power being used to charge my inductor or discharge my inductor. So I kind of see a way to figure out what the energy storage in an inductor must be. I don't really think you need me for this anymore, do you? Prove it. I'll help you out in one way. Current builds from 0 to some maximum sustained current. That's got to be when we've reached our maximum amount of stored energy. So what does this equal? So 1/2 L I max squared. Now, truth is, you could put any value in here. That would be the current amount of energy stored in the capacitor, assuming it was beginning from 0 amount of storage. So putting the max here is somewhat redundant. And the truth is, and be careful with this, the truth is, with an inductor, since it's based on whatever the instantaneous current is, 1/2 L lowercase I squared is just fine here. Because the amount of energy is going to be based on whatever the instantaneous current is at that moment. That will be how much energy is stored in the inductor. The device, although transient, meaning that it's based on whatever the current is, isn't based on an accumulated amount of current like a capacitor is. Everybody follow along with that idea? Charge is different than current. Current is passing through. So add that to your list of things, because now you know that one of the questions that can be asked is how much energy is stored in the inductor at any one time. And knowing this also means that you can probably figure out other information about your circuit, bless you, later on. So I don't think I need to write everything, but power, I squared R for a resistor, amount of energy stored in a capacitor, Q squared over 2C, or 1/2 CV squared. You only get one from me a day, unless I was a different person. So our three circuit elements are three discussions about power usage or energy storage. All right? So that was a bit of an aside, but I wanted to make sure we had covered it. Again, we got it? All right. Discharging an inductor. The problem with discharging an inductor is that in order to discharge an inductor successfully, you have to maintain the current in the inductor until you get to your transition circuit where you'll be discharging. There's a number of ways to do this, but the one that I want to talk to you about is going to be pictured here. I just hope I can do it justice in my drawing. Yep. Not doing a great justice, but I'm trying. There. All right, so inductor, terrible resistor, and an EMF. This is what's known as a make before break switch, where the new connection is made before we break the old connection. A make before break switch. Sometimes they will just put MBB switch. Most of the time on the AP exam, I've seen them use the phrase make before break and write the whole thing out. But it's a special kind of switch that is designed to not create the new connection before, to not break the old connection before making the new connection. This ensures that the current passing through the inductor is maintained at the instant the new circuit is being made. So they will refer to this switch and then refer to the states of the switch the way it's there. That the switch will be in the A position and then move to the B position. And this is the circuit symbol you tend to see. I've used a situation in which a quarter turn switch is here, but there are situations where there's a full half turn to go from one side to the other. It really depends on the nature of how the switch is designed and what you're trying to do with your circuit, but this is what a make before break switch would look like. Now, we've talked about the fact that in a circuit like this, you can be in the charging side. And in the charging side, you get an expression that looks something like that for the charging side current. Where in general, I max would be, for this circuit, the EMF over R. So, in discharging our circuit, unlike the capacitor, where we assume the capacitor begins at a certain charge, with our inductor, we assume that when we throw the switch, the inductor has a certain current in it at time zero. So for this switch, when we throw the switch, right now the current would be passing this way through the switch, and the amount of current would be E over R, or if you want to make this easier on us, we can just write I max. The moment the switch is thrown into the B position, we have a single loop through our circuit with just 2 voltage drops in that loop. So the discharge relationship is going to come from throwing the switch into B after we've reached the steady state condition. And at that instant, we'll have the voltage drop across the resistor and the voltage drop across the inductor, and they will sum to be equal to 0. It's not really short-circuiting. You're closing the circuit through the resistor. And you're allowing the energy in the inductor to push current through the resistor as the magnetic field is collapsing. Does that make sense, Emil?
Yeah, I guess I kind of just saw it as like shorting the circuit right before disconnecting it.
No, if you think, no, it's not shorting this. Oh, you mean because of this? This loop that's in here?
Yeah.
Yes. I mean, technically that part's true. You're shorting the battery, though. I wouldn't say you're shorting the circuit.
Shorting the battery.
You're shorting the battery, right. But it also means that for a split second while you're throwing the circuit, you're maintaining the current going through the inductor because you're maintaining the potential difference for the other side of the circuit. But you're right. When you close this switch, you would be shorting the battery. Just so you guys know, in real circuits like this, for that instant that you would be in this vicinity, you are shorting the battery so the battery discharges through its own internal resistance. On some batteries, that can be very dangerous. And tomorrow we're going to look at a simple use of an inductor kind of circuit and ways to protect circuits like this. There are ways to protect a circuit like this so that you can use the energy in the inductor without having any harmful side effects to the battery. Also, understand this is the schematic for a make before break switch. That doesn't mean that's actually how it's done. Does everybody understand? There's lots of ways to make a switch that might be more modern than just having 2 pieces of metal that happen to be in contact so a third can join them together. You understand what I'm saying? There are other ways to make the switch. This is just the schematic version of what it looks like. I would like to believe that you could figure this out without my assistance. I would really like to believe that. Can you, Jeremy?